So to understand Brauer groups, one first need to know what's a central simple algebra. So for the first part, I will try to stick with the case of a field. So for the first part, I will only be focusing on Brauer group is K, where K will be a field. And so this is the notation. And later we will go to more general version instead of field. For example, we will go to local game and later first field. So maybe so in future I can call these groups as Brauer group of points for obvious reasons because the field has just the one prime value. So there is just a point. The field is just so, anyway, so I was saying to understand Brauer group, one first need to know what's a central simple algebra, at least for Brauer group. So So for me, K will be the field through. So that is just fix this notation once and for all. At least for the first few videos, this is the notation, the field, whenever I will get. So central simple group is a, so say I will denote it by A. So that is my central simple group over this field. It's called central simple if it is simple as in it has no two-sided ideal except the zero ideal and the full ring, and the center of this can be identified with that is what a central simple algebra, and we'll be only dealing with finite dimensional algebra. So a very easy example of such a thing is the matrix algebra for any. So that is a very easy example. And now we know by the you can also classify the central simple algebra due to the Artin-Waterburn theorem. So what does Artin-Waterburn say? It says that whenever you have a semi-simple ring, in a semi-simple ring is always isomorphic to product of matrix rings over division. So that will look like product of matrix rings over division. And if in particular R is just a simple ring, then it will look like just matrix ring over division. So there is just only one factor because it is simple. And semi-simple means like the direct sum of simple. So you can say that for fields, the central simple algebra has a very nice description in terms of matrix. So in order to define Brauer group, what one does is you take all such central simple algebras of various finite dimensions, you vary it over for any one. You take all the central simple algebras of that dimension over the field, and you define an equivalence relation as follows. So let's take two central simple algebra And we know by the previous theorem that both of them will look like matrix ring over some division algebra. Let me call the division algebra corresponding to A is D subscript A, and for B is uh, B subscript B. That is A and that is N prime. It could be different because we are like allowing all the dimensions as long as they are common. And now we define the equivalence. We say A and B are equivalent if and only these dA and dB are isomorphic. And one can easily check that that defines an equivalence relation. So this defines an equivalence relation on the set of all central simple algebra elements. And one can show that a tensor product of two central simple algebra is another central simple. So under tensor product, this is closed. So you take it as a binary operation and you define Brauer Group of Q as the central simple algebra inverse K modulo the equivalence and with respect to tensor as the operation. So that will be my Brauer group of Q. And so because tensor product commutes, it's an abelian group. So abelian is an easy observation. And as an example, if you take C or in general any algebraically closed field, then it turns out that this group is just true because that so for an algebraically closed field, there are no non-trivial central simple algebras over it because it is already algebraically closed. So uh, then the Brauer group has to be just trivial. By the way, we have not said how does the identity element look. So there's an equivalent way one can define this Brauer group. So that is first way. And one can show that both of them are equivalent. It will follow easily because of this RT nodal. So alternatively, again on the set of central simple algebras over K, you pick two elements of this set and you would say they are equivalent if and only if there exists two positive integers such that A tensor with this is actually isomorphic to B tensor with this. And these two are so these two definitions are actually same. These two equivalence due to RT method. That's easy exercise. And again, you define Brauer group as with respect to this relation, and this is an equivalence. This defines the equivalence. And from here now you can easily see what's the identity element look like because you take the, as I said, the only example that I gave of the central simple algebra. So see, all these matrix algebra uh, are in a single class because of this equivalence relation. for all n, they are in one place. So that as a whole is just one element in the Brauer, and that is actually the uh, identity element under tensor that follows directly from this second alternate definition, or from the first if you just think it further. And that is the identity. And now, secondly, so because we are saying it's a group, so there has to be the inverse for each element. So for any element to look like an equivalence class, so for any element, the inverse will be the opposite element. So there is nothing but the multiplication operation is just being reversed. So x and y. So as I said, it is same, but the multiplication operation is just y times. So dot denotes the multiplication in E. So that is and that is because A tensor A out is just endomorphism. And how do you show it? So you take one element A from here, one element B from here, a simple tensor like this, and you send it to this map. It's going to A. Now then you can check that the actually defines an isomorphism. That is so, okay. So that is how one defines uh, the Brauer group for a field. However, there is one more fact about this group which is not evident from this definition. So that is this is Brauer group of key is always torsion, meaning that each element will have finite order. That is not obvious from this definition. So for that we need another alternate definition which is actually more useful in practice. So we'll come to it later. But before that, let me give you another example of a central simple algebra which is not a matrix. So that is a general class of example, the so-called quaternion, which is just to start with any field of so characteristic other than two, field characteristic not two, and you take two element A comma B non-zero, and you define them as generated by x comma y such that x square is A, y square is B, and x square is minus x. So that you can show it's a central simple algebra. And we say that a central simple algebra that is isomorphic to matrix algebra is a P. So for that we have this following easy description of when this quaternion algebra is split. A comma B is split Then, so by the way, the following are equal. Following are equal. Second is, so there is a norm function on this quaternion algebra, which one defines as estimated value. So any typical element, because it is generated by x and y, will look like uh, something like this. And you define it with p square, p square a, r square b plus s square a times. So that is how we define the norm element. And so a comma b split if and only if norm has a non-trivial zero. Non-trivial zero means there is some non-zero element in the quaternion algebra, so that norm of that thing is zero. And third is b is should have b is norm of some element in this quadratic extension of the field. So the square root of a is basically x from this. These three are equivalent, and we'll see why they are equivalent next time. But before that, let me define one more thing, that for any central simple algebra, there is always a splitting field. That means, so for any central simple algebra, over K, there exists a field extension let's say L of K, such that when you base change for any central simple algebra, let's call it A, A tensor L over Q is just matrix algebra. And that is, the existence of such thing is obvious because one may go through the algebraic closure of the separable closure. Because then there is no division algebras over algebraic. So, the existence of such thing is obvious, and that is called a splitting field because A tensor L is the identity element in that block. What is not obvious is that following, that this splitting field one can always choose to be separable over K. So one can choose L as above to be separable over K. That is not obvious, but that is really useful because then once you have such a separable splitting field, you can go to its normal closure. That will give you a Galois extension. And once you have a Galois group in play, things become much more interesting because then you can talk about much more structure than the central simple or in particular Brauer, which I will uh, tell you next time, and also proof of this value, which is just some manipulation and some. So